Welcome to Building Robodoc, an idiot's guide to artificial intelligence in healthcare. Last time we covered the basic theory behind machine learning. Or at least we covered the basic theory behind supervised machine learning, but let's not worry about that distinction too much for now. To distill it down into the simplest possible terms, supervised learning involves showing a computer a task and letting it stab away until it gets it right. Simple though that may sound, we're going to start to talk about some of the amazing things that it has made possible, starting with self-driving cars. There are lots of reasons to love the idea of self-driving cars, from the fact that they could allow us to watch TV during our drive to work, to the fact that they could offer an unprecedented level of independence to those suffering from blindness and other disabilities. But the key issue is, of course, safety. Road traffic accidents are one of the leading causes of death and serious injury in developed societies, and there's every reason to believe that driverless cars will ultimately be much safer than their human-controlled counterparts. Until recently, however, self-driving cars were little more than a pipe dream. The problem wasn't necessarily in creating the brain for the car, because in actual fact the rules of driving are fairly easy to articulate and therefore fairly easy to write into computer code. But rather the major obstacle lay in creating the eyes for the car. An autonomous vehicle would need to be able to process images from at least 2 onboard cameras in real time and with an extremely high degree of accuracy. If you do want an example of what happens when the image processing on self-driving cars goes wrong, look up the tragic story of a guy whose Tesla didn't register the presence of a white truck crossing an American freeway against the background of a white sky, and unfortunately he lost his life as a consequence. Anyway, there didn't seem to be a hope of achieving this level of performance using conventional image processing techniques as recently as 10 or 15 years ago. Luckily, we've already established that machine learning has revolutionized what's possible in the world of computer vision. So let's look at how you might go about applying it to creating a self-driving car. Let's in fact say that you're the head of R&D at Tesla, and you've been given a large budget to create a car-driving AI. The first thing you want is training data. So to acquire this, you decide to equip 1,000 cars with onboard cameras. We'll say 3 cameras each, and have them each driven by humans for 1,000 hours while you capture and store the images. That's 1 million driver hours, and if we assume each camera takes 1 image every 2 seconds, that's over 5 billion images. Now I have plucked those figures out of the air to make a point, but hopefully you can see that it is possible to collect massive amounts of training data in a field like this. Now let's say that each image was then labelled by a human being. Only, instead of simple zeros and ones representing the presence or absence of a single object like our cat versus no cat example from the last episode, this time our human labellers are going to draw a box around any object of interest. So let's say I've been hired as an image labeller and the image I've been given contains a red traffic light, which is on this list of objects of interest. I will draw a box around the traffic light, probably just using a mouse to sort of drag and drop a square box, and this will be called a bounding box. And I will then label this bounding box as containing a red light. Behind the scenes, my label will be stored as a long list of numbers. So let's say that there are a total of 20 possible objects of interest that I'm supposed to be looking for during this labeling task. Let's also say that the red traffic light is the only one of those 20 objects of interest that appears in this particular image. And finally, we'll say for the sake of argument that the term red traffic light is the 17th entry on that list of objects of interest. What happens then is this. Each object is represented by a list of 9 numbers. The first of those 9 numbers is a 0 or a 1, denoting the presence or absence of that particular object within the image, just like with our cat, no cat classifier. If the object is absent from the image, so if that first number is a 0, the following 8 numbers don't matter at all. However, if the object is present, which is to say the first of those 9 numbers is a 1, the following 8 numbers represent the coordinates of the bounding box of that object. So the x coordinate of the top left corner, followed by the y coordinate of the top left corner, followed by the coordinates of the other 3 corners. So hopefully you'll agree that's 8 coordinates in total. then all those 20 blocks of 9 numbers representing the 20 objects of interest on our list are just written down in a long line of 180 numbers in total, which you might hear referred to as a 180-dimensional vector. Just means a list of 180 numbers. In our example, the red traffic light was entry 17 on our list of objects of interest. So because 17 times 9, because of the blocks of 9 numbers, equals 153, the label for our image will consist of 152 zeros, followed by a 1 to show that there is a red traffic light, followed by the 8 numbers representing the coordinates of the bounding box that I drew, followed by a load more zeros till we get to number 180. Of course, our image was just one of the 5 billion training images that we acquired and labelled. So now we've got 5 billion raw image matrices and 5 billion corresponding labels. And we want to find a set of mathematical equations that will consistently get us from the one to the other. Or in other words, we want a set of mathematical equations that will map from the one to the other, because these equations will form a mathematical roadmap from our source data to our desired labels. So we call this data mapping. Hopefully by now you can see that this is just a slightly more complicated version of our cat versus no cat classifier. All we need to do is make a machine learning model that, instead of mapping an image matrix to a single number between 0 and 1, can now map it to a list of 180 numbers. The fact that it's a more complicated mathematical task does mean that you need more training data, and it also means you're going to need more processing power and the training period is going to take longer. But the underlying theory stays essentially the same, and this really will work. By the time our machine learning model is fully trained, it will be able to take any image from our car's onboard cameras. Each image, by the way, is a three-dimensional matrix containing a jumble of over 1 million numbers, so this is no mean feat. And our trained machine learning model will be able to present any image to our car's AI brain in a meaningful way, i.e., there's a red traffic light at position such and such. This then allows us to hard code our car's AI with the rules for driving using conventional computing logic. So for example, if there is a red traffic light ahead of you, then apply the brakes. And this if-then logic gate is sort of the building block of conventional computer code. But here's an interesting thought. Why bother hard coding a set of driving rules at all? Because instead of labelling each image with the objects of interest contained therein, why not simply label the image with the actions that the human car driver was taking at the time that the image was acquired? By which I mean a list of numbers representing, say, the angle of rotation of the steering wheel, the degree of depression of the accelerator or brake pedal, and so on. It's an attractive thought because it saves a massive amount of work in terms of programming the instructions for driving, because our machine learning model should in theory just directly learn how to drive a car without us having to tell it anything about the rules that govern the process of driving. And it's also kind of a neat idea having an AI learn the whole process of driving just by watching humans do it. Unfortunately, there are two big problems with this setup, which you might call an end-to-end approach, because we would be using machine learning to get right from our source data to our final desired task, which is actually controlling a car. Firstly, machine learning models suffer from something we call the black box effect. This is to say that the set of calculations our model would generate to map from the raw camera image matrices to the corresponding driving commands would be incredibly complicated and way beyond anything us humans could hope to make sense of. Incidentally, I've mentioned already the film The Matrix, that the native guys in The Matrix can in theory look at these massive lists of numbers and actually see meaningful images from them. Of course, we can't remotely do that, so it's very difficult to understand what a trained machine learning model is actually doing that allows it to complete the task that you've set for it. So we can't know for sure that there aren't any strange quirks in the system. Let's say, for example, that through pure coincidence, every time an image from our car's onboard camera contained a blackbird in flight, the car happened to be turning left. Our machine learning model may therefore have deduced that the presence of a blackbird is a cue to turn the car to the left, which seems perfectly reasonable from the machine learning model's point of view, because it doesn't have a comprehensive worldview or a human-level intelligence. The only data it's got to inform itself with is that which we've given it. Trouble is that because this knowledge, in inverted commas, is encoded in incredibly complex mathematical equations, we humans are unlikely to notice this quirk until we're testing our new Tesla and it veers into a hedge at the sight of a bird. The second problem with this end-to-end approach bears a little more explanation, and it's going to lead us into hopefully some interesting discussions about some of the barriers to applying AI to healthcare. So we're going to save that until the next episode. So we'll see you then.